All right, 2.1, graphs of sine and cosine functions. So we're going to learn how to graph sine and cosine, including all of their details and properties, as well as also transforming them. So everything all at once, but we've learned about transformations before, so hopefully it won't be too overwhelming. A periodic function is a function that's one that repeats. I'm not sure if this definition, let me read through it exactly. A function f is said to be periodic if there's a real number p so that f of x plus p equals f of x for all real numbers x in the domain of f. The smallest such positive number p, if it exists, is called the period. So in a nutshell, what that's trying to say is the, trying to remember what the definition is I used in secondary 3 when I taught it. Y values repeat every certain distance, length, interval. I don't know, I'll say interval of x values. I don't know if that makes more sense, but basically your graph repeats over and over and over. And it's the y values that keep repeating over a certain length of x. So you go a certain length of x, and then you repeat the graph again, and then you repeat it again. So that length of the graph along the x-axis is called the period, the repeat. Okay, so let's get down some definitions for these. Oh, I changed up my notes a little bit. So I guess I'm going to be kind of making these up out of my head as we go. These just basic definitions. Okay, so the period is the length, horizontal length. Should we say horizontal length? I think that's better. Horizontal length of one repetition. I don't think I spelled that right. Of the graph. Did I spell repetition right? Is that supposed to be an E? Repetition? I'm not sure. Okay. A cycle is one repetition of the graph. Shouldn't use a word if I can't spell it, huh? My computer made a strange noise, like something was disconnecting. I'm trying to figure out if everything's still connected. Ivy can still see my screen, and my screen is still up. Okay, no idea. All right, amplitude is half the distance from minimum to maximum y values. Because if you remember from Math 1050 when we learned about minimum and maximum, those are the minimum and maximum refers to the y values. The x values only tell us where those minimums and maximums happen, but they are the high and low points in the graph. And then the midline is halfway between the min and max. All right, let's look at the sine graph specifically. So we're going to take the ratios we have been learning and graph them. It might be easier to change them to decimals as we go. So we'll do that. Are you guys good with my definitions that I pulled out of my head for these? I think they generally work. Okay, here we go. Sine. So I've got values of sine to find from the angle equals 0 to the angle equals 9 pi fourths. So basically it's going to 2 pi and then a little bit more, just to kind of see what happens there. So then I'm hoping I copied this over properly. Yes, notice how my graph itself doesn't have any increments for pi fourths. So pi fourths, just like on our circle, would be exactly halfway between pi sixths and pi thirds. So I just didn't like scale those in there. So if you need to, between your thirds and sixths, you can throw in a little mark. It'll be your pi fourths. So what's happening here is we've got a function. Our input or our domain value is an angle. And our output or our range value is a ratio. So plug in an angle, get out a ratio. All right, so we're going to start with the sine of 0. Those of you who practiced that little chart today, it was probably a good idea, because what is the sine of 0? If you don't remember, maybe look at your little chart that you're filling out, or look at the back of your blue paper if you've done any of that, or look at the little yellow chart that's just quadrant 1 that's in your note cards. Otherwise, we are trying to memorize these, but if you need to refer to one to make sure we've got the right numbers, or if you want to use a calculator, you can do it that way too. Just notice that I've got this set up with radians, so make sure your calculator's in radians or you're typing them in degrees. So the sine of 0, if everyone agrees, is 0. Is that true? Sine of 0 is 0. If we take the sine of an angle 0, we get a ratio of 0. So now when we graph that, the x value is the angle and the y value is the ratio. So that's just going to be a point at 0, 0 on our graph. So we have two different graphs now that we're going to start working with. We have the graph of the unit circle, which is where we draw our triangles and figure out our ratios. But now we're going to take the relationship between the angles and the ratios and create an xy coordinate graph out of each of our functions. So don't mix up the difference between those two graphs. One of them was finding the ratios and the other one is showing the relationship between the angles and the ratios, right? Okay, pi 6, so 30 degrees. What's the sine of 30 degrees? Isn't that the one that's 0.5 or 1/2? Okay, so you can see on my graph here, I scaled it so that you can put at pi 6, you can put a dot there at about 1/2. It might be interesting to you that my graph only goes up to 1. There's a reason for that, because sine is opposite over hypotenuse, and the opposite leg is always going to be shorter, or if it's a quadrantal angle, equal to the hypotenuse, which means doing a ratio of opposite over hypotenuse is never going to give us a number bigger than 1, right? So that means our graph doesn't need to be taller than 1. Okay, pi fourths. Pi fourths is square root of 2 over 2, but how do you graph a number like that? So what is the equivalent decimal for square root of 2 over 2? So that'll be approximately 0.7. So if this point is at 1/2, then this would be like 0.75. So 0.7 might be just a little bit less than that, maybe about right there. And then again, our pi fourths angle is halfway in between pi 6 and pi thirds. All right, pi thirds. What's the sine of 60 degrees or the sine of pi thirds? Good job. Okay, so let's find the decimal equivalent for that so we know where to plot it. So square root of 3 over 2, it's like 0.86, 0.87. So that is, right here is our x value. This was 0.75. So half of that, it would be about half, wouldn't it? I'm not sure if I'm scaling these properly. Somewhere in there. This isn't quite rounding out the way I want it to, so I'm not sure. Maybe this one should have been a little higher. Okay. Then we have pi halves. Pi halves. What's the sine of pi halves? Sine of 90 degrees. 1. Okay, this reminds me of a stupid pickup line that I have to admit I've nerdily used on dates, and that is, are you the sine of 90? Well, actually, jokingly, but are you the sine of 90? Because I think you're the 1. Huh. I know, it's terrible. Okay, if you remember that joke, though, you'll never forget the sine of 90 is 1. The more ridiculous something is, the easier it is to remember. Okay, so there we are, 1/2 and 1. All right, remember our little all students take calculus. What happens to our sine values in quadrant 2? Are they positive? Are they negative? All students take calculus. Sine is the x value. No, it's the y value. So the y value in quadrant 2 is positive, isn't it? Sine is positive in quadrant 2? Okay, so it's the same. See the bottom number of our radians? We're going to get the same ratio except maybe negative, depending on what quadrant it's in. So since this is quadrant 2, pi thirds and 2 pi thirds are exactly the same number. So that would be our 0.87. So if we go over here to 2 pi thirds, we're dropping down to exactly the same point we had over here. And then 3 pi fourths drops down to like 0.71. So that would be between the thirds and the sixths. So that would be like right in here somewhere. And then 5 pi 6 is back down to 1/2. So that puts our point about right here. And then sine of pi, sine of 180. What's the y value? 0. So far we have this mountain looking thing. Let's keep going, because I think things change a little bit here, and we're not quite done with one cycle of our graph yet. Okay, I decided to start skipping the pi thirds and pi sixths, but they're still the ones that are listed on your graph, so if you're just going to graph pi fourths and pi halves, you're going to have to mark those pi fourths in for sure. So 5 pi fourths is still going to be the same as 3 pi fourths and pi fourths, square root of 2 over 2, except what changes? It is negative, yeah, so that's going to be negative 0.7. So that takes this point down. If this is negative 1/2, then negative 0.7 will be about there. And then 3 pi halves takes us down to negative 1. So that's here, around there. And then 7 pi fourths would be between 5 pi thirds and 11 pi sixths, right? And that should go back up to negative 0.7, so about right there again. And then 2 pi is back to 0, and the sine of 0 is 0. Sine of 2 pi is 0. What would happen when we go over to 9 pi fourths? If you said the whole thing's going to repeat all over again, you are correct. Because remember, angles are infinite. Angles from negative infinity to positive infinity. Because we can do coterminal angles where we add 2 pi or subtract 2 pi infinitely many times. So this graph just keeps continuing forever. But it does repeat with this pattern, which is why we call it periodic, and I'm not quite hitting my points exactly. Ugh. Sometimes I do better at graphing this than others. It should be nice and smooth. Has a weird spot right there. I don't like it. That's a little better. Okay. Oh, my eraser should have been smaller. Oh, that's not too bad, right? Okay, let's talk about the properties of a sine function. I haven't left you a lot of room for these. Um, I am going to give you a little card. I can actually give that to you now. Darn it, Ivy, you won't have this card till you can come get it. But where you can put the actual properties on the card. So maybe let me pause and hand those